18 billion, that's how many elevator trips Americans take every year, and the number that almost never makes the news is how few of them end badly. Hollywood has kept the opposite story alive for decades. Cable snaps, car drops, numbers count down while everyone grabs the walls. Good cinema, bad physics. The last documented elevator freefall happened in 1932, which puts the actual safety record somewhere between very good and statistically almost impossible to beat. That record didn't happen by accident. It's engineering, layers of it, each one designed around the assumption that the layer above it might someday fail. This is what that system actually looks like. Go back to 1852, to a factory in Yonkers, New York, where a craftsman named Elisha Graves Otis had been sent to install machinery and built something nobody asked for, a lifting platform with an automatic brake that locked the car in place the instant a cable broke. The problem was convincing anyone it worked. That's where P.T. Barnum came in, paying Otis $100 to demonstrate at the Crystal Palace in New York City in May of 1854. Otis rode the platform up above the crowd and gave the signal. An assistant cut the rope with an axe. The platform dropped a few inches, stopped cold. Otis looked out and said, "All safe, gentlemen, all safe." 8 elevators sold that year, 15 the year after. By March 23, 1857, one was running passengers in a New York City building whose clientele included Mary Todd Lincoln, and by 1889, Otis equipment was going up inside the Eiffel Tower. Otis himself never saw it. He died 4 months after securing his patent at 49 from diphtheria. His 2 sons took over and within a decade had installed 2,000 elevators across the country. The safety elevator didn't just catch falling platforms, it made the skyscraper a thing people could actually use. Engineers call the whole system a safety chain, a deliberate reversal of the usual metaphor. In a regular chain, one bad link breaks everything. Here, one bad link stops everything. That's the point. Start with the cables. Each rope wraps multiple steel strands under high tension, and a single rope already holds enough to support the car and its counterweight alone. But elevators run 4 to 8 simultaneously, and under a SEMI A17.1 in the US and N81 to 20/50ths in Europe, every cable has to carry 12 times the car's maximum load, all of them at once. For every cable to fail simultaneously under normal operation isn't a realistic scenario. Next, the counterweight on the opposite side of the shaft, sized to match the car's weight plus 40 to 50% of the passenger load. On most trips, the motor is just managing the difference between the two sides. Then the overspeed governor, a spinning pulley in the machine room that turns at the exact same speed as the car. The moment the car drops too fast, flyweights inside swing outward, triple latch, and grab a separate steel rope. That rope yanks the emergency brakes on the car into the guide rails. The car clamps, stops. Below all of that, hydraulic or spring-loaded buffers at the bottom of the shaft convert whatever kinetic energy remains into heat, and a falling car in a sealed shaft compresses the air beneath it, building pressure that slows the descent on its own. 5 separate systems. Any one of them stops a free fall alone. All 5 have to fail at the same moment for anything to go wrong. In practice, that doesn't happen. Saturday morning, July 28, 1945. AB 25. Mitchell bomber flying at 200 miles per hour through dense fog over Manhattan got disoriented and hit floors 78 and 79 of the Empire State Building head-on. The impact severed elevator cables through multiple shafts. A 20-year-old elevator operator named Betty Lou Oliver was badly burned in the crash. Rescue workers put her in a nearby elevator to bring her down, not knowing the bomber had cut those cables too. She dropped 75 floors, roughly 1,000 feet. She survived. The emergency brakes engaged. Severed cables piled at the bottom of the shaft absorbed the car's momentum like a coiled spring. Compressed air beneath her in the sealed shaft added a second cushion on impact. She described it herself. "I started yelling and pounding on the floor. I was going down so fast that I just had to hang onto the sides of the elevator to keep from floating. 3 breaks in her back, 7 fractures in her right leg, a cut eye, burns, concussion, shock. She recovered." Betty Lou Oliver holds the Guinness World Record for the longest surviving elevator fall, proof that when almost everything around the system fails, the system itself can still hold. About 17,000 elevator-related injuries happen in the U.S. every year, and around 30 people die. Real numbers, but the causes look almost nothing like the movie version. Door malfunctions, cars stopping an inch or two above floor level, trips while stepping in or out, which accounts for more than half of all elevator fatalities, freefall barely registers in the data, and half of all elevator deaths don't happen to passengers at all. They happen to installers and maintenance workers who carry the sixth highest workplace death rate in the construction trades, almost entirely from falling into open shafts during routine work, not runaway cars. Open shafts? Statistically, by the time you stepped into an elevator today, you'd already survived the most dangerous part of the trip, the staircase you walked past on the way there. 900,000 elevators are running right now in the United States. The global industry sits around $80 billion, and 8 million elevators worldwide are past their scheduled upgrade window, a number expected to clear 10 million by 2030. The next generation of safety is already being installed. Sensors that track cable tension, motor load, and brake performance in real time, flagging problems before they become failures. Otis, which hit its 170th year in business in 2023, is running integrations with Microsoft Azure to make that kind of monitoring standard. On the experimental end, pneumatic elevators remove cables entirely, the car rides in a sealed tube. A turbine pulls air out from above, and atmospheric pressure from below does the lifting. But whatever the technology, the principle Otis proved with an axe in 1854 hasn't changed. The goal was never to build something that couldn't break. It was to build something where every failure mode has a catch beneath it, so that for anything to go genuinely wrong, everything has to go wrong at once. In nearly 2 centuries of passenger elevators, that hasn't happened. Not luck, not magic, a safety chain, and the rule that one broken link stops everything cold.